Now let us look at this problem. There is a man in a box and he is standing on a weighing scale. And in the first part of the problem, he is applying a force such that he managed to keep the entire thing at rest. The mass of the man is 60 kg. The mass of the box is 30 kg. We have to find the reading of the weighing scale. So we draw the free body diagram of the man. Since he is having mass, his weight will be acting vertically downwards, 60 g. Since he is resting on a surface, normal reaction will act perpendicular to the surface. Since it is connected to a string, tension will act along the string. So therefore, N plus T will be equal to 60 g, since acceleration is 0. Right? Now let us look at the box. The weight of the box will act vertically downwards, 30 g. Tension will act along the string. Now, since this box is exerting a force N on the man will exert an equal and opposite force on the box. So N will act vertically downwards. So T will become N plus 30g. These are equation number 2. We substitute 2 in equation number 1. We get N plus N plus 30g is equal to 60g. So this is 30g, this is 2n. So n becomes 15g. And that is what the weighing scale will show. And this is equivalent to a mass of 15 kg. Now in the second part of the problem, we have to find the force that the man has to apply so that the weighing scale shows his correct weight. So in that case, he has to apply a greater force, and he will accelerate up, and the box also will accelerate up with the same acceleration. So the man will be accelerating up, the box also is accelerating up. So net force is in the upward direction. N plus T minus 60g is equal to 68. Now for the weighing machine to show the correct weight, the normal reaction must become equal to 60g. So N is equal to 60g. So this N also must be 60g. So we get 60g plus T minus 60g equal to 68. This cancels out. So T becomes 60 into A. This is equation number 1. Now write the equation for the box. Tension is upward, normal, and 30g is acting down. So tension must be equal to 60 plus 30, 90g. No, tension minus 90g will be equal to 38. Because acceleration is there in the upward direction. So tension minus 90g equal to 38. Now tension itself is 68. So 68 minus 90g equal to 38. Then this side we get 38 equal to 90g. A becomes 3g. Now once acceleration is 3g, we can find tension, because tension is 68. So tension will be 68. That is 60 into 3g, 180g. So this tension will be equal to 1800 Newton if g is taken as 10 meter per second square. And that is the force the man has to apply on the rope. Now let us try to understand constraint equations. Constraint equations give us the relationship between velocity and objects, or various objects connected by strings. First let us take a simple case to understand the process. So you got a pulley, mass M1 is hanging here, mass M2 is hanging here. The first step is to draw a reference line at the topmost pulley. Remember, all distances are measured from the reference line. After you have drawn the reference line, call the distance to M1 as x1 and distance to M2 as x2. As these masses move, the length of the string must remain constant. So x1 plus x2 must remain constant. So x1 plus x2 is equal to length of the string, and that must remain constant. If you differentiate this equation with respect to time, you get v1 plus v2 equal to 0, because differentiation of a constant with respect to time will be 0. So this implies v2 is equal to minus v1. That means velocity of m2 is minus the velocity of m1. That is very obvious, right? Again, if we differentiate this equation with respect to time, we will get a2 equal to minus a1. So this is how we get the relationship between velocity and acceleration for this simple case. Now let us consider a slightly more complicated case. So I got one pulley here, and there is another pulley here which is movable. Mass M1 is here, mass M2 is here, mass M3 is here. We have to find the relationship between acceleration of M1, acceleration of M2 and acceleration of M3. So first we draw a reference line at the topmost pulley. All distances are measured from the reference line. Call the distance to M1 as x1, distance to M2 as x2, and distance to M3 as x3, and distance to this pulley as x4. Okay, x1 relates to m1, x2 to m2, x3 to m3. If you follow this nomenclature, life will be simple. So now, as the masses move, length of both the strings remain constant. So now let us look at the first string. The length of this left hand side is x1. Length of the right hand side is x4. So x1 plus x4 is equal to L1, and that will remain constant. So if we differentiate this equation twice with respect to time, we get A1 plus A4 is equal to 0. This implies A4 is equal to minus A1. Right? Now let us look at the second string. The left hand right side of this second string is this much in length, and this is x2 minus x4. So x2 minus x4 plus the right hand side of the string is this much in length, and that is x3 minus x4. This will be equal to the length of the second string. This gives us x2 plus x3 minus 2x4 is equal to L2. Right? Again, if we differentiate this equation twice with respect to time, A2 plus A3 minus 2A4 will give you 0. A4 is minus A1. Therefore, A2 plus A3 plus 2A1 equal to 0. So this is the constraint equation. 2A1 plus A2 plus A3 equal to 0.